humans would like to understand their origins. We'd like to understand how life arose on Earth.
And now science believes it has the answers. It's even built the biggest machine on Earth to recreate the beginning of time. Take a virtual shuttle ride back to the Big Bang. Our universe is an elegant ensemble of over 1 billion galaxies, each cradling some 100 billion stars. It's still uncertain how many planets exist. We know Earth takes up residence in the Milky Way galaxy. Our blue planet orbits our sun like a sapphire jewel, the only celestial body known thus far to harbor life. But how did our world get here in the first place?
Ultimately, we want to understand what it was that produced the universe and how it evolved over the 14 billion years of its existence.
For the first time in history, scientists have answers to some of these questions, in the sense that the universe is everything that we know about, everything that we see. And what the Big Bang does is tell us, how did we get here?
The Big Bang Theory says that over 13.7 billion years ago, our universe began at an incredibly dense, hot, compressed state with one main mission: expansion.
There was a cosmic explosion that created the stars, the heavens, the galaxies around us. So everywhere we look, we see remnants of this cosmic explosion which set into motion the universe.
The Big Bang is now a well-accepted physical theory to explain what happened after our universe was born. It's substantiated with sound scientific data and observations.
A theory isn't just any old idea that you dream up in the middle of the night. Only after it has satisfied many tests does it get elevated to the status of a theory.
If you look at the Big Bang Theory, we just don't have one data point. We have hundreds of data points that fit exactly the Big Bang Theory.
When we look up into the night sky, we can rewind time all the way back to the Big Bang itself. When you first look up in the sky, you see stars, and you might even see our own Milky Way galaxy. But if you look still farther away, you see the cluster of galaxies. Looking back even further still, you can see the very first generation of stars being formed and dying. If we keep going back in time, we can see the very first atoms forming. Continuing our journey back in time, we can see the formation of the first protons and neutrons. If we keep rewinding the clock much further past that, we can look back to the very first instant of the Big Bang.
How was the discovery of the Big Bang achieved? Why do we know it to be true? And what do we have left to learn? For hundreds of years, astronomers have stared into the starry night and contemplated the origin of the universe. But most ideas contained religious undertones. By the 20th century, science finally began to assemble the pieces of this age-old puzzle. In 1915, Albert Einstein, perhaps the most influential scientist of our time, was fascinated with our universe. To him, there wasn't a beginning or ending. Einstein believed the universe was infinite and eternal. Yet Einstein's personal beliefs contradicted his equations that indicated the universe had a beginning. Einstein's theory of general relativity predicts that gravity is woven into the fabric of space and time, or space-time. When introducing mass into a stationary universe, gravity will eventually pull all the matter in the universe together, In other words, galaxies would fall on top of each other. On the other hand, the universe can be expanding if it was born in a state of expansion.
Einstein thought that the universe is static, and such a hypothesis was aesthetically pleasing to him. So he actually introduced a mathematical fudge factor into his equations that didn't make them wrong, but gave a very special solution, a very unlikely solution, a static universe.
Einstein called this fudge factor the cosmological constant. The physicist proposed that there's a repulsive effect to counter gravity to maintain a static universe. This cosmic variable satisfied the scientific community, who at the time had a narrower view of our world.
If you were to ask an astronomer back then, what is this universe of ours? They would say, that's easy. It's just the Milky Way galaxy. That's all there is. It's not moving. It's simply uniform and static.
Einstein's ideal model of a static universe was soon shattered. In the 1920s, at Mount Wilson Observatory in California, astronomer Edwin Hubble peered through the biggest reflecting telescope of its time. It enabled him to look farther into space than ever before. Hubble was amazed to discover that there were thousands of galaxies beyond our Milky Way. He did this by measuring the brightness of distant stars compared to stars close by when observing their red-shifted electromagnetic radiation.
Everybody's familiar with the sound that a car makes when it drives by you, as it passes. That's the wavelength of sound being stretched as the car is receding or approaching you. Light waves also do the same thing. When an object is moving toward us, it becomes bluer. And when an object is moving away from us, it appears reddened. This is called redshift. So by observing how red something appears to be, astronomers can get an idea of its distance.
So here's a hypothetical universe expanding after the Big Bang. It's kind of like our universe, where the stickers are the galaxies and the rubber is the space in which the galaxies are embedded. This is exactly what we see in our universe, where the galaxies are moving away from one another.
Hubble proved what Einstein's calculations had long predicted, but what the scientific genius was reluctant to acknowledge.
But then when Edwin Hubble finally showed that the universe was in fact expanding, Einstein said, this was my greatest blunder.
Hubble's discovery of an expanding universe, known as Hubble's law, became the first piece of evidence that would support the Big Bang, a theory that came from an unlikely source. Georges Lemaitre, a Belgian priest and physics professor, had studied Einstein's equations. He calculated if the universe is expanding today, it must have been smaller in the past. Therefore, it must have had a beginning. Lemaitre proposed that our expanding universe emerged from a primeval atom.
He understood the implications of Einstein's idea that if the universe is expanding, then perhaps it had an origin in some kind of cosmic primordial atom or some kind of cosmic egg that hatched, giving birth to the universe.
Georges Lemaitre's colleagues did not think much of the primeval atom. It suggested a creation event which perhaps borders more on religion and theology. They preferred that the universe either be static, as most people had thought before that, or perhaps eternally expanding, if it really is expanding, as Hubble showed.
Lemaitre defended his primeval egg theory as purely scientific. But British astronomer Fred Hoyle staunchly opposed his hypothesis. While he agreed the universe is expanding, Hoyle proposed that new galaxies are formed from matter that is constantly being made. So the universe has always existed and always looked the same. Hoyle called his alternative theory the steady-state model.
Fred Hoyle, in fact, accepted the observed fact that the universe appears to be expanding. But he said there was no creation event, there was no beginning. The universe has always been expanding, and it will forever continue to expand.
In 1949, during a London radio show, Hoyle tried to contrast his steady-state model with Lemaitr's idea of a primeval egg. He referred to Lemaitr's theory of the Big Bang idea, and the name stuck. These two competing theories would become engaged in the ultimate scientific duel to determine the origin of everything. By the middle of the 20th century, the origin of our universe was still a big question mark. Two opposing theories were at the heated core of this scientific battle. Fred Hoyle's steady-state model and Georges Lemaitr's Big Bang idea. In order for either of these theories to be proven, each must explain the origin of elements in the universe, the stuff that everything is made up of. There are light elements, primarily hydrogen and helium, and heavy elements, such as nitrogen, carbon, oxygen, and iron. Under high temperatures, the light element of hydrogen fuses to form helium. In turn, helium fuses into the heavier elements. Fred Hoyle proposed that the creation of all these elements, heavier than hydrogen, happened in the cores of fiery stars in a process called nuclear fusion. This also included the second most abundant element, helium.
Willie Fowler, who's a nuclear physicist, and Fred Hoyle, they explained how stars make the elements. And so then they thought, well, stars also make helium, so you could just make all the elements in stars, and you didn't need to have a Big Bang.
But Hoyle's theory had several glaring problems. Most importantly, it didn't explain how hydrogen was formed, because the earliest stars must have been formed with hydrogen already present. Hoyle dismissed this problem by suggesting that hydrogen and helium had always existed and were always spontaneously being created. But others began questioning Hoyle's hypothesis. In the 1940s, Russian physicist George Gamow also studied the origins of chemical elements. Using the Big Bang theory, he predicted the relative proportions of hydrogen and helium in the universe, and found that it should contain a lot of helium, which only can be created by fusing together two hydrogen atoms. Gamow discovered that hydrogen makes up nearly 75% of the elements in our universe, and helium only 25%. He concluded that stars alone couldn't generate so much helium. But if the universe began with a hot, dense Big Bang, temperatures would have been high enough everywhere to fuse hydrogen into helium.
If you look at what's called primordial clouds of gas, they have what is probably the original proportion of hydrogen and helium. And that's roughly 3/4 to 1/4 hydrogen to helium. And that's what the Big Bang theory predicts.
The origin of heavy elements from the fusion of lighter elements became known as nucleosynthesis. It's the second line of evidence supporting the Big Bang theory. But George Gamow went one step further.
Physicist George Gamow and his students made a fantastic, startling hypothesis. If the universe was very hot at the instant of the Big Bang, then today there should be an ember, an afterglow, echoes of this radiation still reverberating around our universe. The temperature of outer space should be a few degrees above absolute zero, a remnant of the fierce, blistering temperatures of the Big Bang itself.
Gamow didn't attempt to detect this afterglow, but he was onto something. 2 decades passed before the Big Bang theory was undeniably proven, and by accident. In the 1960s, AT&T, formerly Bell Labs, built a giant antenna to communicate with the earliest satellites. These instruments convert sound waves into electrical impulses and then into light in the form of microwaves and radio waves. In 1964, radio astronomers Robert Wilson and Arno Penzias were using the antenna to observe hydrogen in the Milky Way galaxy when they picked up a strange signal. Using the Giant Horn telescope located in Holmdel, New Jersey, Penzias and Wilson scanned the sky to search for this pesky sound. To their shock, they picked up a faint radiation signal in all directions. The astronomers were perplexed. They knew of nothing in space that could create such noise.
Most scientists probably would have ignored it, but they felt that this was something serious. They had looked into all possible causes, including pigeons and their droppings on their radio telescope.
But as it turned out, there wasn't anything artificially causing the noise. This signal really does come from the universe itself. And when they saw it, they eventually got in touch with an astronomer at Princeton who had actually theorized that it would be possible to observe this microwave background directly.
Penzias and Wilson discovered the smoking gun. It was the cosmic microwave background, the actual leftover radiation from the Big Bang, as predicted by physicist George Gamow back in the late 1940s. The cosmic microwave background shows what the universe was like approximately 380,000 years after the Big Bang. Prior to that time, the universe was a dense, opaque stew of charged particles and radiation in the form of gamma rays and X-rays. After about 380,000 years had passed, the primeval mixture cooled to allow the first neutral atoms to form. At this time, matter and radiation became separate, and the first photons, or rays of light, were able to pass freely through the universe. Those same photons are the glowing radiation we see today that has journeyed since early times.
It's like when you go camping in the mountains and there's a morning fog and you can't see anything until the sun comes up and the fog burns away. And then you can see beautiful mountains around you. It doesn't mean that the mountains were just made a few minutes ago. And so that's what's happening in the universe. So 400,000 years after the Big Bang, the fog cleared out, and then we can see the structures. But we think the structures were actually made back in the first fraction of a second after the Big Bang.
The cosmic microwave background radiation was the third and strongest piece of evidence validating the Big Bang model.
The death knell, in a sense, to the steady-state theory was the discovery of the cosmic microwave background radiation. The steady-state theory basically has no plausible origin for this diffuse radio radiation.
The scientific community finally embraced the Big Bang theory. But the cosmic microwave background immediately generated questions. When looking closely, the radiation appeared smooth, not lumpy as expected.
This was a problem because we look at the universe today and we see that it's obviously not uniform. There are galaxies in some places and not in others. And so it became a problem for cosmologists to explain how could the structure have evolved out of this initial, very smooth state.
Over the next 3 decades, scientists tried to find tiny temperature variations or fluctuations that would leave an imprint on the cosmic microwave background. But these variations were difficult to see with ground-based instruments. Science would need to blast into space to search for the answers. For decades after its discovery, scientists tried to figure out why the cosmic microwave background radiation, the afterglow from the Big Bang, wasn't painting a true picture of what our universe actually looks like. It looked perfectly smooth, so how could we get stars and galaxies from such a uniform beginning? In 2001, NASA finally pioneered the Wilkinson Microwave Anisotropy Probe, or WMAP. This second-generation satellite produced a series of speckled maps, which provided a cosmic blueprint for the evolution of our universe. WMAP measured tiny variations in temperature density of the cosmic microwave background. These temperature irregularities eventually led to the formation of today's clusters and superclusters of galaxies.
There was hot spots that were 30 millionths of a degree hotter and cold spots 30 millionths of a degree colder. These lumps basically tell us that there are clumps of matter early in the history of the universe that could then provide the seeds around which clusters of galaxies collapse.
WMAP also helped to confirm the age of the universe, between 13.7 and 13.8 billion years. But even with the information gathered from WMAP, there were still big problems with the Big Bang Theory. The cosmic microwave background revealed that the temperature in space was oddly uniform. Distant regions have the same temperature, yet they're 90 billion light years apart.
In the Big Bang Theory, there is still some loose end. If you look in this direction, and you look in that direction, then in principle, you're looking at two pieces of the universe that should not be connected to each other. There was not enough time since the beginning of the universe for these 2 points to be in contact with each other.
To solve this cosmic quandary, a theory called inflation was introduced. Hubble's law proved that our universe has been expanding since the beginning of time. However, 1/1,000,000,000 of a trillionth of a trillionth of a second after the moment of creation, space itself went through a brief hyper-expansionary period, whereby it expanded faster than the speed of light, and then returned to a normal expansionary pace. Consequently, points in space which are now far away could have once been in close contact with each other and the same temperature.
The universe started out really small. That means there was time for it to become uniform, to reach the same temperature and density everywhere, because it was small. Inflation exponentially made space grow into a giant size. By exponentially, I mean doubling in size every tiny interval of time. And then, as it expanded, it maintained a uniform temperature and density.
Inflation theory also helps to explain another problem. The data from WMAP determined the shape of the universe to be flat and not curved as it should be, based on the amount of matter and energy present.
The theory of inflation naturally explains this apparent flatness of the universe. Imagine we live on the surface of this basketball, which is pretty small, so it looks obviously curved. Now suppose you blow the basketball up to the size of the Earth. Well, any locally visible region would look flat. They look flat only because we're seeing a tiny fraction of all that there is. Well, in the case of the universe, astronomers think that it may well be curved like a basketball. But it's so enormous that we see only a tiny fraction. So locally, the part that we see looks flat, despite the intrinsic curvature. The flatness problem is solved because regardless of the initial shape of the universe, once it has expanded to a structure far larger than the parts that we can see, the parts we can see are naturally flat.
Inflation neatly solves many of the issues surrounding the original Big Bang model. But there's only one problem. There's still no proof that inflation actually happened.
We've got the idea that the universe started off in a hot, dense state and is expanding. That's the Big Bang idea. We've got an idea now that we add to it called inflation about how part of that process worked. We still don't have the detailed, this happened, this happened, this happened. We still have to explain why it's the way it is.
A new mission may discover if inflation truly occurred. In 2009, the European Space Agency, in conjunction with NASA, will launch Planck. It's a third-generation satellite that will study the cosmic microwave background with incredible resolution that hasn't been achieved by the COBE and WMAP missions.
If you go to the amusement park and you look at yourself in one of those funny mirrors, the image that you see of yourself is distorted. But since you know what you're supposed to look like, you can sort of infer that that mirror was distorted. With Planck, we'll be able to see distortions of that. And from those distortions, we'll be able to learn something not just about the early universe, but something about the matter in the present-day universe.
Scientists are trying to prove inflation existed by finding something it may have left behind. Gravitational waves are vibrations in the fabric of space-time that are emitted from moving objects. Einstein predicted gravitational waves exist, but they've never been directly observed. Yet if inflation truly occurred, the energetic expansionary event should have sounded out a gravity wave that's still ringing to this day.
Of course, there's no sound in space, but you can imagine that just as a particular thickness and length of violin string produces a particular note or frequency, so a particular type of astrophysical event would produce a distinct signature in gravity waves. And we think that the Big Bang actually produced a very unique signature of gravitational waves that scientists are hoping to detect today.
Gravity waves produced by the Big Bang would leave a particular imprint on the cosmic microwave background called polarization.
We might be able to detect a certain pattern of the polarization that would indicate gravitational waves in the early universe. And those gravitational waves would be a direct indication of inflation and the mechanism that caused it.
These gravity waves from inflation would have persisted from those first fractions of a second and would still be around. They would leave a pattern imprinted on the cosmic microwave background that is unique. It's distinct from any of the other processes that would have been going on in the universe at that time.
At the South Pole, astrophysicist John Kovac and his team will be installing a second-generation telescope called BICEP 2. It will measure the polarization of photons from the cosmic microwave background. A photon, or particle of light, is sometimes polarized, meaning it wiggles in a certain direction. If inflation produced a gravity wave, it would have created a swirl pattern in the polarized part of the microwave background that the BICEP 2 receiver will feasibly pick up.
We come to the South Pole with the BICEP telescope, like most of the microwave telescopes down here, for the extraordinarily clear, dry atmosphere. There is virtually no water vapor above your head at the South Pole because the atmosphere is so thin and so cold. Any presence of water vapor in the atmosphere will soak up those photons from the early universe and confuse us with the false signal. We try to go where the air doesn't get in our way from those photons in the early universe. Short of going into space, the South Pole is the best that we can do.
BICEP 2 is equipped with sensitive microwave sensors to measure fainter levels of photons, which might hold a signal of a gravity wave produced by inflation.
It amazes me that here at the South Pole, we believe that we have the capability to test this theory with a small telescope. The telescope mount will allow us to steer our telescope around, point it to any point on the sky. We stare at one patch of the sky, collecting photons relentlessly, building up a picture of what that polarization looks like on that small patch of sky over the course of months and years that becomes increasingly clear.
The existence of gravitational waves in the cosmic microwave background may prove that inflation propelled the brief hyperexpansionary period of our universe.
Inflationary gravity waves provides us with such a smoking gun. Those gravity waves would be observable today in the pattern that they would imprint on the polarization of the cosmic microwave background. It would be conclusive evidence that inflation is the right picture for how the universe began.
Experiments at the South Pole may take us back further in time than science has ever imagined. But can we go back farther, even before the period of inflation, to the actual moment of creation?
One of our problems with our cosmology model today is that they don't address exactly what is happening at the instant of the Big Bang. When matter is compressed into that highly condensed state, our laws of physics actually don't work.
Scientists do not yet understand what came before inflation, or what caused the Big Bang itself. So what happened before the period of inflation remains a mystery for now.
One of the features of inflation is that it tends to erase any evidence of what happened before. So somebody could have written down on a blackboard, and then somebody else could have erased it, in which case it's of no use. But if you didn't erase it entirely, then there might be some tiny little traces. And what we're starting to think about now is whether there might have been some tiny traces of the pre-inflationary universe that might still remain even after inflation.
On the border of Switzerland and France, the physics laboratory called CERN houses the biggest, most complex scientific machine ever assembled. Housed 300 feet underground and the size of 5 jumbo jets, the Large Hadron Collider, or LHC, was designed to recreate the conditions that existed a millionth of a second after the Big Bang, to provide answers about why and how it happened. Subatomic particles called protons are sent whizzing around a 17-mile-long underground circular path in opposite directions at over 99.9% the speed of light. 4 detectors stationed within the tunnel act like cameras to record the collisions. As protons smack together, their mass and velocity combined will hopefully form new particles that may have been present nanoseconds after the Big Bang and have since decayed. These particles could shed light on the origin of fundamental particles of nature.
We're looking for new particles. It may be that these new particles live for only a brief instant in time and decay into other particles, and we observe those decay particles, and we track them back, and from that we can find out what their energy was, where they came from, and what the mass of the parent particle was.
As lead project manager at CERN, physicist Michael Tutz remains hopeful that experiments will produce Higgs boson, known as the God particle. It's long been thought that the Higgs particle may have been present an instant after the Big Bang and may have given mass to all the normal matter in the universe.
One of the primary reasons for building the LHC was to discover this Higgs particle, which in some sense is kind of the holy grail of particle physics, because it's the last remaining piece of the puzzle for which we don't have experimental evidence.
The Large Hadron Collider may also shed light on the theory of everything. It proposes that under extremely high energies and temperatures, the 4 forces of nature, gravity, electromagnetic force, the strong and weak nuclear forces, could have once been unified in the early moments after the birth of the universe. Then, when gravity split off from this master force, it kick-started the rapid expansionary period of inflation, which can be thought of as being the bang in the Big Bang.
At the very early stages of the universe, when the energies were very high, it might be that all of the forces seem to have the same strength, because that suggests that maybe, in fact, all the forces we see now are manifestations of some more sort of primordial, earlier force that existed.
Did some earlier force exist to create the Big Bang? And if so, where did it come from?
Inflationary theory does more than just fit the data. It also predicts there could be a pre-inflationary period. It says that if the Big Bang happened once, it could happen again, and again, and again, and again.
Many theoretical physicists subscribe to a pre-Big Bang, where our universe may have actually spawned from a pre-existing universe.
One idea for what happened before the Big Bang is that really there was another universe and we were a quantum fluctuation out of that pre-existing universe. And this can happen many times.
If the universe was born once, it could happen again, creating a multiverse of universes. Perhaps they happen all the time. With universes pumping into other universes, creating bigger universes, or universes splitting apart into two baby universes.
The pre-Big Bang models really don't have experimental data to back them up. And so they might be true, and they might not be true.
There's still no evidence confirming whether our universe began from nothing or something. But the Big Bang sheds light on how our universe has evolved. And perhaps its ultimate fate. The Big Bang is the accepted explanation of the origin of our universe. According to scientific data, observations, and theories of physics and mathematics, here's a timetable of what we think happened. The universe began in a hot, dense, tiny state, and began to expand. If the theory of everything is proven, the four forces of nature, gravity, electromagnetism, the strong and weak nuclear forces are unified into one fundamental force at 1/1,000,000,000 of a trillionth of a trillionth of a second. As the universe continues to expand and cool, gravity suddenly separates from the three other forces. At the same time, the universe expands from a tiny portion of a proton's diameter to over 1 billion light years across in a fraction of a second. This hyper-expansion process, called inflation, lays out the seeds of structure throughout the universe and locks in their nearly uniform temperature. As inflation subsides, the electroweak and strong nuclear forces become separate forces. They interact with a sea of particles and antiparticles to create a cosmic soup of energy. 100 seconds after the Big Bang, temperatures drop to 1 billion degrees. Protons and neutrons fuse together by the strong nuclear force to create the nuclei of heavy hydrogen. Driven by the intense temperature and pressure, nuclear fusion further converts the nuclei of heavy hydrogen into helium. After a few minutes, about 1/4 of the hydrogen is converted into helium, which in turn will produce heavier elements. For hundreds of thousands of years, matter and radiation are unified in a cosmic fog. Then, at 380,000 years after the Big Bang, matter and radiation separate, letting photons, or rays of light, to travel unhindered through space. The foggy universe becomes transparent, allowing the photons that make up the cosmic microwave background to be seen. When the universe is a few 100 million years old, gravity draws hydrogen and helium gas together to form clouds that collapse, forming the first stars. When the universe is about 500 million years old, groups of stars and gas form the first galaxies. As galaxies cluster together under the force of gravity, the first stars die and release newly formed heavy elements: carbon, nitrogen, and oxygen, the building blocks of life. These heavy elements eventually meld to form new stars. Over 9 billion years after the Big Bang, our sun forms within a cloud of gas in the Milky Way galaxy. Remnant gas and dust particles swirl around the sun and stick together to form the planets in our solar system, including Earth. Everything we see on our planet emerged from stardust that originated over 13.7 billion years ago in a sudden spark of energy.
You could consider our sun the grandchild, if you will, of the very first generation of stars that were formed right after the Big Bang.
But what does the Big Bang model foretell about the future of our universe? One theory is that as our universe continues to expand, matter will spread thinner and thinner. Galaxies will exhaust their gas supply to form new stars, and old stars will burn out. The universe will become dark and unbearably cold.
At some distant point in the future, the universe will be so cold that even life itself cannot live in a frozen universe.
The Big Bang model is one of the scientific triumphs of the last 100 years. Through intense scrutiny and struggle, science has now mapped out a virtual shuttle ride back to almost the beginning of time. And the quest continues as new discoveries will shed light on why we're here and where we came from.